Welcome to the deep dive. Today, we're trying something ambitious. We're looking straight into the mind of Stephen Hawking.
Yeah, specifically through his final collection of thoughts. These are from speeches, interviews, essays gathered after he passed.
And he was tackling the really big questions, wasn't he? Existence, the universe.
Exactly. It's more than just physics, though. He was really attempting this, well, grand synthesis, trying to use the rational tools we have, general relativity, quantum mechanics, to build a complete picture.
A theory of everything.
Right. And, crucially for him, one that was totally self-contained. To, in his words, eliminate the need for a divine creator intervening.
He pursued that with intense rigor, but also that famous wit. I always think of that Eddie Redmayne story.
Oh, yeah? What do you
Redmayne played him in the movie, and apparently he nervously mentioned they shared a birthday sign, a zodiac sign.
Huh.
And Hawking just instantly replied through his speech device, "I'm an astronomer, not an astrologer."
Perfect. Sets the tone, doesn't it? Very clear line drawn.
Definitely. So that's the kind of thinking we're exploring today.
Yeah, we'll trace his path. Start with how he mathematically defined the beginning of time. Then dive into his really radical work on black holes.
And finally, pull it together with his argument for how the universe might just be, well, the ultimate free lunch.
Exactly. A self-creating system.
Okay, let's start there then. The beginning of his career, which was also about the beginning of time itself.
It was quite poetic, actually. He was born exactly 300 years after Galileo died. He mentioned that sometimes.
Huh.
And apparently, as a kid, he was always taking things apart. Got the nickname Einstein at school, though he did say his practical abilities never matched up to my theoretical qualities.
A theorist from the start.
Seems so. And that theoretical power really exploded in 1965 at Cambridge. He took Einstein's general relativity.
Which describes gravity, the big structures.
Right. And he combined it with some really cutting-edge mathematics from Roger Penrose.
And that combination led to
His first major proof. Basically, if the universe is expanding now, which we see it is, then if you run the clock backwards, everything must have come from a single point of infinite density.
the singularity.
A singularity. A mathematical proof that the universe, say 10 to 15 billion years ago, had a definite beginning. The Big Bang.
Wow. And what's incredible is that this huge intellectual achievement happened right around the time he got his diagnosis.
Yeah, motor neuron disease, ALS. They gave him just 2 years.
That must have been devastating.
It was a massive turning point. He admitted he'd been a bit, anti-work at Oxford before that, but the diagnosis kind of reset everything, reduced his expectations to zero, as he put it.
And that.
Well, the disease progressed slower than predicted, and that sense of borrowed time turned into this incredible drive. He realized that tackling these immense questions was his way of saying, while there's life, there is hope.
Amazing. He basically raced against time, using his mind when his body was failing.
Absolutely. Even after the tracheostomy, losing his voice completely. First, spelling words with eyebrow movements, then that famous chi-controlled computer system, ACAT.
And he kept working on singularities, didn't he? Not just the Big Bang.
That's right. The same mathematical ideas he used for the universe's beginning, he turned towards the end state of massive stars. Black holes.
Okay, so black holes. Before Hawking, what was the picture?
The classic idea came from John Wheeler, who actually coined the term black hole in '67. They were seen as these simple objects, just the remnants of collapsed stars.
Defined by just mass, spin, and charge, right?
Exactly. Mass, angular momentum, and electric charge.
Yeah.
That's it. It led to the no-hair theorem.
Meaning they couldn't have any other unique features? No bumps or, well, hair?
Precisely. They were thought to be incredibly simple. But Hawking, he complicated things. In a good way.
How so?
Connected them to thermodynamics, heat, disorder, entropy. Around 1970, just after his daughter Lucy was born, actually.
Yeah.
He proved something called the area theorem. It says the surface area of a black hole's event horizon, its boundary, can only ever increase, or stay the same. It never shrinks.
Okay. And that reminded him of entropy, which also only increases in a closed system.
Exactly. It was this huge hint that black holes weren't just gravitational objects. They might follow the laws of heat, too.
But the really mind-bending part came a few years later in '74.
Oh, yeah. That was the big one. Spurred on by some work from Soviet physicists Zeldovich and Starobinsky. Hawking realized something radical. If black holes have entropy and follow thermodynamic laws, they must have a temperature.
Wait, a temperature? But they're black holes. Nothing escapes. How can they be hot?
That's the paradox. And if they have a temperature, they must radiate energy. like a hot poker glows.
So black holes aren't actually black.
Not completely. This was the discovery of Hawking radiation. It showed they emit particles, they radiate, they glow, just incredibly faintly, as if they were only slightly warm. It blew people's minds. It merged general relativity, quantum mechanics, thermodynamics.
And the formula for that temperature, it's actually on his headstone in Westminster Abbey, isn't it?
It is. Shows how fundamental it's considered.
But I'm still stuck on how. How does anything get out?
Okay, the explanation usually involves quantum mechanics.
Mm-hmm.
You know how empty space isn't really empty? There are these virtual particles and antiparticles popping into existence and vanishing again almost instantly.
Uh-huh. Quantum foam, sort of?
Sort of. Well, imagine a pair pops into existence right at the edge, the event horizon. One particle falls in, but its partner escapes out.
And the one that falls in?
It carries negative energy into the black hole, effectively reducing the black hole's mass. The one that escapes carries positive energy away. That escaping particle is the Hawking radiation.
So the black hole isn't radiating its own substance, but it's losing mass because these negative energy particles are falling in, and it slowly evaporates.
Over unimaginably long timescales, yes. It shrinks and eventually disappears.
Wow. Okay, but you said this led to another problem.
A huge one. The information paradox. This might be Hawking's most profound puzzle left unsolved, really.
What's the paradox?
Well, if the blank hole evaporates completely, what happens to all the information about the things that fell into it? You know, the specific arrangement of atoms in a book or an astronaut? Their quantum state.
Doesn't it just get destroyed, become random heat?
That's what Hawking initially argued, and it seems logical. But a fundamental law of quantum mechanics says information cannot be destroyed. It has to be conserved, preserved somehow.
So his own theory about radiation seemed to violate another core law of physics.
Exactly. If information is truly lost, then quantum mechanics, which is basically the operating system of reality at the smallest scales, is fundamentally wrong or incomplete. It means the universe isn't perfectly predictable. It's a massive headache for physicists.
And they're still wrestling with that one.
Oh, absolutely. Trying to figure out how information could escape or if it's stored somehow. It's pushing the boundaries of quantum gravity research. Okay, that's a deep puzzle. Which brings us, I guess, to his final big philosophical argument. If the laws of physics are this powerful, maybe even paradoxical, where does God fit in? Or does God fit in at all?
Right. This is where he brings it all together. He always maintained that asking if God exists is a perfectly valid scientific question.
But he defined knowing the mind of God differently, didn't he?
Yeah, for him it meant knowing the complete set of laws of nature. If you have those laws, and they're comprehensive, do you need anything else to explain why the universe is the way it is?
His answer was leaning towards no, I take it.
Pretty strongly. He simplified the recipe for the universe down to basically 3 ingredients: matter, energy, and space.
Okay.
Then, using Einstein's UMCQ, he argued matter is just a form of energy. So you really only need 2 things, energy and space.
All right, energy and space, but where did they come from? You still need something to provide them, don't you?
Not necessarily if the total energy budget is 0. This was his key insight.
0? How can it be 0? Look around, there's clearly stuff, energy. But he used this great analogy. Imagine you want to build a hill that's all the positive energy, the stars, the galaxies, us. To get the dirt for the hill, you have to dig a hole next to it.
Okay.
That hole represents negative energy. And he argued that space itself, specifically the energy bound up in gravitational fields, acts like a vast reservoir of negative energy.
So for every bit of positive energy hill that exists,
There's an equal amount of negative energy hole in the fabric of space-time due to gravity. The two perfectly cancel out. The total energy of the universe is exactly 0.
it all adds up to nothing.
Precisely. And if the total energy is 0, you didn't need to borrow any net energy to create it in the first place. Therefore, quote, the universe is the ultimate free lunch. It could pop into existence from nothing without violating conservation of energy.
But hang on, if it adds up to 0, why is there a hill and a hole at all? Why didn't they just stay canceled out as nothing? What keeps them separated?
Well, that separation, that structure we see, that's a consequence of the way the universe unfolded after the Big Bang, the inflation period. But the fundamental point for him was the 0 balance. The system is closed.
And the laws of physics themselves dictate that beginning, the Big Bang singularity.
Yes. And if the laws say time began at the Big Bang.
Then asking what happened before the Big Bang is meaningless.
Exactly. It's like asking what's north of the North Pole. If time itself didn't exist before that moment, there was no before for a cause or creator to operate in.
Okay, but there's still that awkward singularity point itself, where the math goes infinite, the laws break down. Didn't that still bother him? Didn't it seem like a place where you might need something external, a boundary condition?
It did, and that's where he introduced, with Jim Hartle, the no-boundary proposal. It's perhaps his most abstract idea.
How'd they get around the singularity problem?
They used a mathematical trick, essentially. It
Yeah.
involves something called imaginary time.
Imaginary time. That sounds, well, made up.
It's a mathematical tool, not like another dimension you could visit. Think of it like rotating an axis on a graph. When you plug imaginary numbers like the square root of -1
Right.
into the time component of the equations,
Yeah.
time starts behaving mathematically just like another dimension of space.
So time becomes space-like. What does that do to the beginning?
It smooths it out. Instead of the universe starting at a sharp point, a singularity, which is like an edge where the laws break down. In imaginary time, the beginning looks more like the South Pole on a globe. It's a point on the surface, but it's not an edge or a boundary. It's smooth.
So no sharp beginning, no edge, means no need for boundary conditions, no need for someone to set the rules at the boundary.
That's the profound implication. If the universe has no boundary in imaginary time, it didn't need anything external to kick it off. It's completely self-contained. The ultimate self-starter kit, governed purely by the laws of physics.
Wow. That's a
Yeah.
lot to take in, deriving the lack of need for a creator purely from physics and math.
It is staggering. And it really shapes his legacy, doesn't it? Someone said, Newton gave us answers, Hawking gave us questions, and Hawking's questions themselves keep on giving.
That feels right. And his questions weren't just cosmic, were they? He worried about us too, humanity's future.
He did. He often pointed out this mismatch. Our knowledge stored in books, computers, the internet grows exponentially. But our basic biology, our instincts, shaped by Darwinian evolution, they haven't really changed much.
We still have those caveman impulses, aggression, tribalism.
Pretty much. But now, instead of clubs, we have nuclear weapons, AI, genetic engineering, engineered viruses. He saw that gap between our ancient instincts and our godlike technological power as incredibly dangerous, an existential risk.
Did she see a way out?
He actually speculated about self-designed evolution, using genetic engineering not just for disease, but maybe to improve core human traits, memory, intelligence, but maybe most importantly, to try and curb aggression, to upgrade our mental software to match the hardware we've built.
Controversial, but coming from a place of deep concern.
Definitely. And that concern ties back into the structure of the universe itself, interestingly. Why this universe? Why these laws?
You mean why 3 dimensions of space, for instance? Why this specific setup?
Exactly. He invoked the anthropic principle here, viewed through the lens of M theory.
M theory. That's the candidate for the theory of everything, right? String theory's successor.
Sort of, yeah. M theory suggests that maybe the Big Bang didn't create just one universe, but potentially a huge number, a multiverse, each with slightly different laws or dimensions.
Okay. So why are we in this one?
Well, the anthropic principle basically says the very fact that we are here, conscious beings able to ask this question, limits the possibilities. We could only exist in a universe whose laws and structure allow for life like ours to evolve.
So what's special about 3 spatial dimensions?
It seems to be a sweet spot for complexity. If you only had 2 dimensions, stable, complex structures like, say, animals with guts couldn't really exist topologically. Things would fall apart.
And more than 3, like 4 spatial dimensions.
Then gravity behaves differently. You would follow an inverse cube law, not inverse square. And that makes stable planetary orbits, like Earth around the sun, pretty much impossible. No stable orbits, no long time frames for life to evolve complexity.
So out of all possible universes M theory might allow, only ones that look roughly like ours. 3 large spatial dimensions, stable gravity could possibly contain observers like us to wonder about it.
That's the idea. The laws allow us, but they don't necessarily point to a designer for us. It just reinforces that idea of the ultimate free lunch, a system capable of producing complexity, including us, operating entirely under its own steam.
It really brings it back to us then, doesn't it? If we live in this self-contained universe, this potential free lunch, what do we do with that knowledge, especially given the risks he outlined?
I think his own personal example and his advice is maybe the most powerful takeaway for anyone listening. He faced unimaginable odds.
Yeah.
And his message was always one of persistence and curiosity. I think his own words are the best conclusion. Be brave, be curious, be determined, overcome the odds. It can be done.
A call to action, really, to understand the universe and maybe ourselves a little better, and to figure out how to navigate being potentially the universe's way of thinking about itself.